Hello viewers, in this video we're going to do Cambridge A-Level Further Maths 2, paper 2 for the Pure Maths 2. The syllabus code is 9231 and this is variant 3 from May June 2025 series. We go for question 5 now. The previous questions I've already done and uploaded into the same playlist. So question 5 is using a De Moivre's theorem to show that secant 5 theta is equals to a secant power 5 and all this on the denominator here. Just a quick recall of what De Moivre's theorem is. Let's say we have a complex number z to be equals to a cosine theta and I sine theta. We can write this in the form of e to the I theta, right? And then what De Moivre's theorem says, if we raise this complex number to a power n, then I mean the complex form will or the exponential form, it will look like this n theta, right? Because what happens is that the powers can multiply, and this carries forward such that, or maybe I use a different color to highlight the n here. So we raise it to power n, so the power n is here, and what happens is the cosine and the sine function, the angle, it multiplies together with n also. So this is what De Moivre's theorem states, that if you have a power of n of a complex number, when written in its cosine and sine form, you can just multiply the angle with this power that is being raised to. So in this case, in our case where we have a secant 5 theta and a secant to the power of 5, we can easily guess that we are probably going to deal with a z power of 5. So let's deal with that first. So we let z be an arbitrary complex number, cosine plus I sine theta, and we also let using De Moivre's theorem, we know that z to the power of 5, okay, the 5 I use a red color, z to the power of 5 is cosine of 5 theta added together with I sine 5 theta. Alright, so this one is done. We have proven this so far, and now next what we're going to do is we're going to manually expand using the binomial theorem. So z power of 5 can also be cosine theta I sine theta power of 5, like this. So using the binomial theorem, I hope you guys remember the theorem, right? Where you have x plus y to the power of n, there will be the sum of r equals to 0 to n of n choose r, a or sorry, not a, x power n plus y, not plus, multiply y n minus r. So this is the binomial theorem formula. So we apply this for our z, our complex number, where x is cosine theta and y is I sine theta, and yeah, let's expand this. Alright, for the what we call the combinations, you can type in your calculator, right? But this power of or the increasing power of the imaginary number, you can try and recall also that I power 1, that's just I power 2 is negative 1, I power 3 is negative I power 4 is therefore I, and therefore it continues from here. Sorry, I power 4 is positive 1, my mistake. I power 4 is positive 1, and I power 5 is only, it starts, the cycle repeats, so it's a modulus of 4, or base of 4. So we keep this in mind as we expand all this, the I sine power. Right, this is the complete expansion of the z power 5 using the binomial theorem. what I'm going to do, if you notice that what we have in the equation we're trying to prove is only the secant and secant and secant, right? There's no cosecant or any sine function. Um, and in our case also, we've proven, we're gonna take this result that we have proven from earlier, this one, the z power of 5 using the De Moivre's theorem, and we're also gonna consider the fact that cosine is the real part of the expansion, or the complex number. So therefore, we're also going to take only the real part of this binomial expansion. So, okay, Re, or the real part of z power 5. So I'm just going to discount or ignore all the imaginary parts, and I have cosine power 5. Okay, highlight for you. Cosine power 5, 10 cosine 3 sine squared, and 5 cosine sine 4. So these are the only three terms that are real. I'm going to copy it down first. And what this equates to is, again, is the cosine 5 theta, right? Cosine 5 theta from our De Moivre's theorem. Okay, so yeah, up to here, now, yeah, as I said, we have noticed up here there is no sine function. So what we're going to do is use the Pythagorean identity, where sine squared is 1 minus cosine squared. This is the Pythagorean identity, and we'll yeah, substitute all the values in. I missed also that sine power 4 is the same as sine squared, so that is just 1 minus cosine squared squared. So that is what we are doing at the for the sine power 4. So now we go and expand it again. After expanding, we should arrive here, and it looks like we have the correct coefficients, but we have the wrong powers of things, right? So what we're probably gonna do is, um, yeah, I think first we divide both sides by cosine power of 5, like that, so that we can get the 16. And then this cosine power 3 divide cosine power 5, that will be secant squared. Okay, there's a cosine to the power of -2, and cosine divide by cosine power 5, that gives us secant power of 4. And on this side is a secant power of 5 and cosine power of 5. And what we're going to do is we just divide both sides by, yeah, we do the cross division. So this one goes that side and this one goes that side. And so end up with secant 5 theta on the left hand side, and on the right hand side we have a secant power of 5 divided by whatever is on the left hand side. So 16 minus 20 secant squared 5 secant power of 4. So is it in the same form? Yep, it's exactly the same as what they asked us to prove. So this will be the final answer shown. Alright, so far okay. Now, okay, next part is given this polynomial with order of 5, and they want us to find the roots of this polynomial. So we know polynomial of n order, they will have n number of roots. So straight away we will say there's 5 roots. And what we can notice here is that somehow these three terms, if we factor out 2, you get 5, 20, and 16, which is similar coefficients to what we have in part A. So first, let's isolate some things. We try and notice factor. Yeah, we factorize out first. Maybe we factorize out a -2. Okay, so the coefficients is matching on in this factorized term. It's matching with our secant powers also. Yeah, maybe we move it to one side. And yeah, now okay, on this side we have a x power 5. So we can go ahead and divide, kind of divide by this term, and we isolate the constants on one side. So we have x power 5 divided by this long expression, and we isolate the constant on one side, on the right hand side. So at this point you should be able to see quite clearly that on the left hand side what we have is basically the same form as what we have proven here, but it's just in x. So what we have to do is we let x be a secant theta. So we have secant 5 theta, 5 secant power 4, 20 secant squared, and 16 equals to this. And what we can do is, since we already proven this fact, you can just replace the entire thing with secant 5 theta using De Moivre's theorem, right? We have proven this already. So now this is simply just a trigonometry question where we know the reciprocal identity, that is cosine. So we take the reciprocal of this also, and we know it's positive, so it exists in quadrant 1 and quadrant 4. So we find the basic angle, 5 theta will be equal to, what's the angle? Pi over 6, isn't it? Pi over 6. Or or the fourth quadrant, there will be 11 pi over 6, 2 pi minus the first answer, right? And the way we get the next three roots is by, since we know that obviously the circle you can turn infinitely many rounds, and by 2 pi you'll get the same answer. So there is infinitely many solutions to this question. So all we need to do is add the 2n pi to both solutions, where n is a rational number. Yeah, I believe Z is the symbol for rational numbers. Right, yeah. And so, obviously, according to the question, we have a polynomial of the fifth order. So we need to give five answers. So yeah, maybe we take 3 from the first one and 2 from the second one. So we have pi over 6. That's for n is 0. For n is 1, okay, n equals 0 also, we get this one first. Let's do it in increasing order. Then the n equals to 1, here we have 13 pi over 6. Here for n equals to 1, this side is 20, 20, 25, 23 pi over 6. Then lastly, 25 pi over 6. So after you got all the solutions, and you we find theta already. What does the question want? Where we want the roots in the form of secant q pi. So I mean, all is in terms of pi already. That's what they want in exact form lah. I suspect. So the roots, therefore we can just write x equals to. So yeah, this is the final answers for this form, or yeah, De Moivre's theorem, as well as a polynomial finding the roots. Yeah, thanks for watching.